Hi all, my name is Anjali. In this video, I will be explaining about the concept of hash sort. Before learning hash sort, let's see why we need it. Imagine students searching for their lockers. In the traditional way, they check several lockers one by one, which takes more time and comparisons. Now imagine each student uses the last two digits of their ID to go directly to the correct locker. It's much faster and more efficient. Hash sort works in the same way. Instead of repeatedly comparing elements, it uses a hash function to place each element directly into the slot or cell, reducing comparisons and improving sorting efficiency. Basically, hashing is a technique used to store and retrieve data easily. It works by using a hash function to convert a key into an index in a hash table. This allows us to find or store data much faster than searching through every item. These are the three main components of hashing. First is the key, which is the data we want to store. Next is the hash function, which converts the key into an index. Finally, the hash table stores the value at that index. As we discussed earlier with the school locker analogy, the student's ID is the key. The office assigns the locker number like the hash function, and the locker itself is the hash table where the student's belongings are stored. These are the common types of hash functions. First one is the division method, the next one is the mid-square method, and the last one is digit folding method. In this video, we will deal with each of these methods. The division method is the simplest hashing technique. It finds the storage index by dividing the key by the table size and using the remainder. The remainder becomes the position where the data is stored. Here the key is 16 and the table size is 8. Since 16 divided by 8 leaves a remainder 0, the key is stored at the index 0 in the hash table. The mid-square method works differently. Instead of directly dividing the key, we first square the key. After squaring it, we take the middle digits of the result and those digits become the hash value or index. Let's see how this works with an example. Our key is 3101. First we square it, which gives 9616201. Since the table size is 1000, we need a 3-digit index, so we take the middle 3 digits, which are 162. Therefore, the hash function returns 162 and the key is stored at the index 162 in the table. The digit folding method divides a large key into smaller equal sized parts. These parts are then added together and the final sum becomes the hash value. If needed, the result can be further adjusted to fit within the size of the hash table. Here the key is 124655012. We split it into three parts: 124, 655 and 012. Next we add these numbers together. 124 plus 655 plus 12 equals 791. So the hash function returns 791 and the key is stored at index 791 in the hash table. This method simplifies large keys by breaking them into smaller parts and combining them to generate the storage location. Collision is an important concept that comes under hashing. A collision happens when two different keys are assigned the same index in the hash table. Since only one position is available, we need a way to handle this situation. So we know that collision happens when two different keys are assigned the same index in the hash table. Instead of overwriting the existing value, we use collision resolution techniques to make sure both values can still be stored and accessed correctly. Let's look at the four common techniques. First is chaining. In this method, if two or more keys are assigned the same index, we don't replace the existing value. Instead, we store all the values one after another at the same index. We do this using a linked list, which is a collection of connected nodes where each node stores one value and a link to the next node. So, when a collision happens, a new node is simply added to the end of the list. Later, when we want to receive a value, we go to that index and search through the linked list until we find the required key. The next one is double hashing. This method uses two different hash functions. The first hash function calculates the original index. If that index is already occupied, the second hash function calculates a new position. This helps spread the keys more evenly across the table and reduces the chances of repeated collisions. The third method is linear probing. If the calculated index is already occupied, we simply check the next position in the hash table. If that is also occupied, we continue checking one position at a time until we find an empty slot. It is simple to implement, but it can lead to clustering where many values get stored close together. Finally, we have quadratic probing. This method also looks for another empty position, but instead of checking every next slot, it moves by increasing square values such as 1 square, 2 square, 3 square, and so on. This spreads the keys out more evenly and reduces clustering compared to the linear probing. So, that's all about the theoretical concepts related to hashing.
Hello everyone, I am Varsha. As Anjali has already explained the basic concepts of hashing, including its need, components, hash functions, and applications, I will continue the seminar by explaining how hashing actually works in practice. In my part, I will discuss the hashing algorithm, solve an example problem, explain collisions in hashing, and describe the different collision resolution techniques such as linear probing, quadratic probing, and chaining. Finally, I will demonstrate a C program implementation of hashing and analyze its output. So, let us begin by understanding the hashing algorithm and the steps involved in storing data in a hash table. Before understanding the algorithm, let's first understand the basic idea behind hashing. Hashing works by taking a key and converting it into an index using a mathematical formula called a hash function. The hash function used in our example is h of k equals k modulo m, where k is the key and m is the size of the hash table. Now let's see the algorithm step by step. First, we create a hash table of a fixed size, and next we read the key that needs to be stored. Then we apply the hash function to calculate the index position. After obtaining the index, we check whether that location is empty. If it is empty, we directly store the key there. If the location is already occupied, then a collision has occurred. In that case, we apply a collision resolution technique such as linear probing, quadratic probing, or chaining. Finally, after storing the key successfully, we display the updated hash table. So the main idea is very simple. The hash function tells us where the data should be stored, and if two values try to use the same location, we resolve the collision using suitable methods. Now let's understand hashing using an example. Suppose we want to store three values 25, 32 and 18. The size of the hash table is 10. We use the hash function h of k equals k modulo 10. First let us calculate the index for 25. 25 modulo 10 gives 5. Therefore 25 is stored at index 5. Next 32 modulo 10 gives 2. Therefore 32 is stored at index 2. Similarly 18 modulo 10 gives 8. Therefore 18 is stored at index 8. After storing all values, the hash table contains 32 at index 2, 25 at index 5 and 18 at index 8. This example shows how hashing directly determines the storage location without searching through the entire table. Now let's discuss an important issue in hashing known as collision. A collision occurs when two different keys generate the same hash index. For example, if we use the hash function k modulo 10, then 25 modulo 10 equals 5. 35 modulo 10 also equals 5. Both values want to occupy index 5. Since only one value can be stored in that location, a collision occurs. Collisions are very common in hashing because the number of possible keys is usually much larger than the number of available locations in that hash table. Therefore, we need special technique to handle collisions effectively. To solve collisions, several collision resolution techniques are available. In this seminar, I will discuss three important techniques. The first one is linear probing, the second is quadratic probing, and the third is chaining. Each method has its own advantages and way of handling collisions. Let's look at each one in detail. Linear probing is one of the simplest collision resolution methods. When a collision occurs, instead of storing the values at the occupied location, we check the next position in that table. If that position is also occupied, we continue checking the next locations until an empty position is found. For example, suppose 25 is already stored at index 5. Now we want to insert 35. The hash function again produces index 5. Since index 5 is occupied, we move to index 6. If index 6 is empty, we store 35 there. This process is called linear probing because we move through the table one location at a time in a linear manner. The advantage of this method is its simplicity. However, it may create clusters of data which can reduce efficiency. Then, quadratic probing is another method used to resolve collisions. Instead of checking locations one by one, we move using square increments. The formula used is h of k plus I squared. Suppose index 5 is occupied, first we check 5 plus 1 square which gives 6. If that location is occupied, we check 5 plus 2 squared which gives 9. If we need it, we continue with larger square values. This method spreads data more evenly across the table and reduces clustering compared to linear probing. Therefore, quadratic probing often performs better when many collisions occur. Chaining is completely different approach to handling collisions. Instead of searching for another location, we allow multiple values to exist at the same index. This is usually done using a linked list. For example, suppose 25, 35 and 45 all produces index 5. Instead of moving them elsewhere, we store them together in a linked list connected to index 5. So index 5 will contain 25 followed by 35 followed by 45. The main advantage of chaining is that collisions can be handled without searching for empty locations. However, additional memory is required for the linked list. Now let's see the C program implementation of hashing. In this program, we create a hash table of size 10. Initially, all positions are marked with -1 indicating that they are empty. The values 25, 32 and 18 are stored in an array called keys. Using a loop, each key is processed one by one. For every key, the hash function key modulo 10 is applied. The resulting index is calculated and the value is stored in that position of the hash table. After inserting all the values, another loop is used to display the contents of the hash table. This program demonstrates the basic working of hashing without a collision handling. Then let's examine the output. We can see that values 32 is stored at index 2 and value 25 is stored at index 5. Value 18 is stored at index 8. All other positions contain -1, indicating that they are empty. This output matches the calculations we performed in our example problem, confirming that the hashing process is working correctly. Now let's look at the advantages and disadvantages of hashing. The major advantage is its speed. Searching, insertion, and deletion can usually be performed in constant time, which is order of 1. Hashing is therefore much faster than many traditional searching methods. It is widely used in real world systems where quick data access is required. However, hashing also has some disadvantages. Collisions can occur frequently if the hash function is not designed properly. Performance may decrease when too many collisions occur. In some cases, additional memory is also required for collision handling techniques. Finally, hashing is an efficient technique for storing and retrieving data, and it uses a hash function to convert keys into index positions within a hash table. Although collisions are unavoidable, they can be effectively handled using techniques such as linear probing, quadratic probing, and chaining. Because of its speed and efficiency, hashing is widely used in modern computing applications such as databases, password systems, search engines, and caching. Thank you for your attention.
Myself Anjana P K, first MC. Today I am going to explain odd even sort. It is also called the brick sort. Odd even sort is a simple sorting algorithm. It is similar to bubble sort. It works by comparing swapping neighboring elements in two phases. Odd phase, even phase. The process continues until all elements are arranged in the correct order. It's easy to understand, easy to implement, suitable for parallel processing. Working principle of odd even sort. Odd even sort works in two repeating phases. Odd phase, compare position 1, 2, 3, 4, 5, 6. Swap elements if they are into wrong order. Second phase, even phase. Compare position 0, 1, 2, 3, 4, 5. Swap if needed. These two phases repeat until no swaps are required. This means the array is completely sorted. Odd even sort algorithm. First step, the sorting process begins. Second set sorted false. We assume the array is not yet. This tells the algorithm to start checking the elements. Repeat until sorted in true. The algorithm keeps repeating the sorting step until the array becomes completely sorted. Set sorted true all the beginning of each passes. We assume the array is sorted. If swap happens later, we will change it back to false. Perform odd phase. Compare and swap adjacent elements at odd positions. Perform even phase. Compare and swap adjacent elements at even positions. Compare 9472. New array 49278. Since swaps occurred, the array is not yet sorted. Seventh step, if any swap occurs, set sorted in false. Whenever a swap, this tells the algorithm another pass is needed. If an entire odd phases and even phase finished without any swaps, the algorithm knows the array is already in correct order. Next step, the array is sorted. The process ends and the final sorted array is obtained. Example of first pass of odd even sort. 9, 4, 7 to it the array. Odd phase. In the odd phase, we compare elements in positions 1, 2, 3, 4. Array is 9, 4, 7 to 8. Compare 4, 7. 4 is smaller than 7. They are already in the correct order. No swap needed. Array 9, 4, 7 to 8. Compare 2, 8. 2 is smaller than 8. They are already in the order, in correct order. No swap needed. Even phase. Now compare elements at position 0, 1, 2, 3. Current array 9, 4, 7 to 8. Compare 9, 4. 9 is greater than 4. They are in the wrong order. Compare 7 to 7 is greater than 2. They are in the wrong order. Result after first pass 4, 9, 2, 7, 8. First pass is completed since swaps occurred. The array is not yet sorted. So that algorithm will continue with another odd phase and even phase until no swaps are needed. pass 2. After the first pass, they arrays 4, 9, 2, 7, 8. Odd phase. The odd phase compare position 1, 2 and 3, 4. Current array 9, 4, 9, 2, 7, 8. Compare 9 to 9 is greater than 2. They are in the wrong order. So we swap them. After swapping 4 to 9, 7, 8. Even phase. Now compare position 0, 1 and 2, 3. Current array 4 to 9, 7, 8. Compare 4 to 4 is greater than 2. They are in the wrong order. Swap them. Array becomes 2, 4, 9, 7, 8. Compare 9, 7. 9 is greater than 7. They are in the wrong order. Swap them. Array becomes 2, 4, 9, 2, 4, 7, 9, 8. Result after pass 2, 2, 4, 7, 9, 8. Pass to the algorithm compares and swap adjacent elements again. First 9 and 2 are swapped in the odd phase. Then 4 and 2 and 9 and 7 are swapped in the even phase. After the swaps, the array becomes 2, 4, 7, 9, 8. Final pass. After pass 2, the array is 2, 4, 7, 9, 8. Algorithm performs one more pass to check if all elements are in the correct order. Odd phase, compare elements at position 1, 2 and 3, 4. Current array 2, 4, 7, 9, 8. Compare 4 and 7. 4 is smaller than 7. They are already in the correct order. No swap needed. Array remains 2, 4, 7, 9, 8. Compare 9 and 8. 9 is greater than 8. They are in the wrong order. Even phase. Now compare adjacent elements again. 2, 4 in correct orders. No swap. 7, 8 correct order. No swap. Final result 2, 4, 7, 8, 9. Final pass, the algorithm compare 4 and 7, which is already in the correct order. So no swap is needed. Then it compares 9 and 8. Since 9 is greater than 8, they are swapped. The array becomes 2, 4, 7, 8, 9. After checking again, no more swaps are required. This means all elements are in ascending order. In this odd even sort program and output. Time complexity. Time complexity, the amount of time an algorithm takes to complete its works as the number of elements increases. It helps us measure the efficiency of sorting algorithm. In odd even sort, the time complexity depends on the arrangement of elements in the array. Best case, average case, worst case. Best case occurs when array is already sorted. Average case occurs when the elements are arranged randomly. Worst case when the array is reverse order. Best case 1, 2, 3, 4, 5. In this situation, odd even sort only needs one complete pass to check the elements. It compare adjacent elements. No swap are needed because all elements are already in order. Algorithm detects the no swaps occurred and stops since it only checks each element at once. The number of operations increases linearly with the number of elements. Therefore, the best case is time complexity. Average case 4, 1, 5, 2, 3. In this situation, some elements are in the correct position while others are not. The algorithm must perform several odd and even phases. Many comparisons and swaps are required. Multiple passes are needed before the array becomes completely sorted. As the number of elements increases, the number of comparisons and swaps grows approximately n square. Worst case 5, 4, 3, 2, 1. Every element in the wrong position. Algorithm must perform the maximum number of comparisons and swaps. Odd and even phases are needed to move elements to their correct positions. Sorting process continues until the entire array becomes sorted. As the number of elements increases, number of operations grows approximately n square. Advantage: simple to understand and implement, suitable for parallel processing, easy modification of bubble sort. Disadvantages: inefficient for large data sets, higher execution time compared to advanced sorting algorithms, required multiple passes. Conclusion: odd even sort is a simple sorting algorithm that works by comparing adjacent elements in odd even sort phases. It is easy to learn and implement, but it is not suitable for large data sets because of its higher time complexity. Thank you.